So let's have some introduction to the ethers. Ethers are derived from the alcohol. In the alcohol, if this hydrogen or hydroxy group is replaced, you will get a ROR, right? So therefore ethers are said to be derivatives of the alcohols, just like the carboxylic acid derivatives are acid chlorides and the esters and so on. So ethers is a extension to the alcohols. If at all the alkyl group is an aromatic, you can say phenols. So aromatic ethers also considered as an extension to the phenols. So alcohols, just like the number of carbons, you say alk, ene, ol. So just like in the nomenclature of the alcohols, this part is said to be alk, then saturation An plus with the OL as a function alkanol, just like that. So this is also considered as an alkane containing a alkoxy. So this said as a alkoxy. Alkoxy is a extension group added to the alcohol. Therefore first you finish this just like hydroxy, alkoxy plus alkane. So this alk is referring to the number of carbons in the R. If both are same, you can say methoxy, methane, ethoxy, ethane and so on. But if two different groups are there, one should be careful in which is alkoxy, which is alkane, right? If it is symmetric, like for example methoxy methane, systematic name is methoxy methane. Methoxy methane. Similarly ethoxy and so on. But if one side is a ethyl group, one side is a methyl group, then you cannot say ethoxy methane. You have to say methoxy as a extra group, the longer chain, because as per the nomenclature, IUPAC nomenclature rule 1, longest chain will be the root word. This is my root word, this is extension. So therefore I consider this methoxy group as an extra. So methoxy ethane. Methoxy ethane is the right way, and ethoxy methane will be the wrong name. When both are same, methoxy methane or methoxy methane same, so therefore that is absolute. But in the case of where two different alkyls are there, the longest chain containing, because these two are different root words through separated by the oxygen, so you cannot say prop. So you have to say separately only, but the longest chain will be the main compound and the smaller carbons with oxygen said as a alkoxy, methoxy ethane. Okay. In the case of, like for example, it is also noticed that when the long chain is more than 2 carbons, then you have to number this longest chain. This is 1, 2, 3, because there is another chance that the compound can be like this also. If methoxy is there on the second carbon, now the nomenclature cannot be same for both. This is 1 methoxy propane, this is 2 methoxy propane, main compound is propane. Okay, so 1 methoxy will become a compulsory. If I don't say 1 methoxy, there comes a confusion, just like chloropropane, there is an ambiguity, it can be 1 chloro, can be 2 chloro. In the case of ethane, it's not. So whenever the number of carbons in the main compound increases more than 2 carbons, then this position mentioning is a must. This is a 2 methoxy. 2 methoxy propane, both are propanes, but 1 methoxy, even 1 becomes a necessary in the case of like this. You can't say a methoxy propane. There comes a ambiguity, is the methoxy is on the first carbon or on the second carbon. Therefore the 1 methoxy propane, 2 methoxy propane must be specifically you have to say. In the ethers you have one specific point in the cyclic ethers. In the ethers can be in the ring form. Such ethers are called cyclic ethers. In the cyclic ethers also nomenclature is very interesting. So let us take 1 or 2 points in the cyclic ethers. There can be a small cycle with 2 carbons with oxygen. They are called 3-membered cyclic ethers. Out of that two are carbons, one is alkane. These compounds, whenever it is there, they are said epoxy. Cyclic ethers are started with epoxy. The alkane is ethane, epoxy ethane. In this case, number not necessary. Which two carbons are attached? Means there are only two carbons, so obviously 1 and 2 position not necessary. But when 3 carbons are there, it can be two types. 3 carbons can be like this between the 1 and 2 or between the 1 and 3. So both cannot be the same name. So you can't say epoxy propane for both. Now this is epoxy between 1 and 2. So therefore you have to say 1,2 epoxy propane, and this is called 1,3 epoxy propane. Epoxy, both are propanes, but 1,2 epoxy means between the on propane 1,2 carbons are in the form of epoxy linkage. Okay, the epoxides, epoxy, this system itself, you can have a common name called from ethylene you got it, therefore it is also known as ethylene oxide, or we have this system is also called oxyrane. If a 4-membered ring with oxygen, this is called oxetane. Oxyrane and oxetane. Oxygen, you know, therefore you may say, better say oxygen. Oxyrane and oxetane. And if 4 carbons are there, systematically it is called 1,4 epoxy butane, has got a nomenclature derived from this. This is called a furan. Furan is an aromatic compound, however, but this is equivalent with the saturated system, isn't it? With these 2 double bonds, if it is saturated, you will get this one. So therefore it is called tetrahydrofuran. So tetrahydrofuran is nothing but the 4 carbons with 1 oxygen, a 5-membered ring. Tetrahydrofuran is a common name for this one, but it is originally it is 1,4 epoxy butane, and so on. Complicated systems also can be named like this. For example, there is an oxygen in the center. Now this compound can be named like this: 1, 2, 3, 4, 5, 6, 7. So the compound is considered as a 7-membered long chain. It is written in the cyclic form, but you can write 7 carbons straight, and 2 and 6 is attached. Therefore you say 2,6 epoxy. 2,6 epoxy heptane. The system of this 6-membered with O is called oxane. Cyclohexane with 1 oxygen called oxane. Now if that is the case, numbering will be 1, 2, 3, 4, 5, 6. So that is 2,6 dimethyl oxane. 2,6 means where the numbering starts from the oxygen, then so the 1 to heterocyclic system, always hetero atom will be given 1. So therefore it is called 2 and 6 carbons are attached with methyl. So you can say 2,6 dimethyl. In this case also 2,6. But if it is numbered like this 1, 2, 3, 4, 5, 6, it is also 2,6. So therefore common name will be 2,6 dimethyl. 2,6 dimethyl. This is called cyclohexane, so this is called oxane. Okay, oxane. 2 oxygens, dioxane. 3 oxygens symmetrically, trioxane. They are all common names. So this dimethyl oxane is a common name. However, heptane is the IUPAC nomenclature. So in the cyclic systems, we have common nomenclature like 3-membered rings are oxyrane rings, 4-membered rings are tetrahydrofurans, that is oxetane rings, 5-membered rings are tetrahydrofuran, 6-membered rings are oxanes, and so on. Like that, there are some, the practice it is there in the practice to use the common names also. So we have one question like when 2 methyls are there, systematic name will be the 1, 2, 3. So 1,2 epoxy 2 methyl propane. systematic name will be 1,2-epoxy 2-methyl propane it will be. But it is said that numbering from the oxygen 1, 2, 3, so 2,2-dimethyl oxyrane, 2,2-dimethyl oxyrane is undergoing hydrolysis in acidic medium. Explain the mechanism, that was the question. In such a case, 2-methyl oxyrane means numbering is from oxygen. So in heterocyclic rings, in the common method, heterocyclic rings are numbered from the heteroatom. But whereas in the IUPAC, only the carbons are given 1, 2, 3. So it is the longest chain 1, 2, 3. At 2 we have a methyl between 1 and 2 epoxy. Therefore 1, 2 epoxy and 2 methyl propane will be the systematic name. Like that there is some difference between, definitely carbon common names and the IUPAC names differs. But you must have a both adequate knowledge in the nomenclature of even common methods also, because in the questions common names also being used in the making the questions. Let's go for the preparation methods. A few methods which are useful in the preparing these ethers. The first method will be the from alcohols. This is the classical method. For example, an ethyl alcohol, when you take an ethanol is heated with the concentrated sulfuric acid at about 140 degrees centigrade. The temperature is a specific point here. At 70 degrees just ethyl hydrogen sulfate is formed, but at 140 degrees centigrade, two alcohols loses a water molecule, and then the ethyl and ethyl joins, you will get the diethyl ether. This is what at 140. If the temperature is around 170, the elimination takes place of water takes place from the only from one molecule HOH is removed, and you will get ethylene formation. So therefore the temperature is a very, very important one. Below 140, ethyl hydrogen sulfate, that is ethyl group with the OSOSOOH. This is at around 70 degrees centigrade with the same reagent is same, but at 170 degrees centigrade elimination takes place. So therefore you must be very careful about the temperature. The less temperature is used, you will get some other product. The more temperature is there. So this has got the method has got this problem of temperature maintaining, and it is a reversible reaction also. If it is not separated, you will get back the again alcohol formation. The product is not 100% because the eliminating water molecule, isn't it? So if the flask and all the conditions are not anhydrous conditions, then hydration, that is water addition, takes place, reverse reaction takes place to get back the ethers. Maybe formed ethers undergo hydrolysis to give back the alcohols. So this method is a one industrially it is practicable also, however, but from one side you go on add alcohol, the other side ether will be continuously, you can go on add one side alcohol, the other side ethers will have low boiling point, therefore they will be continuously coming out as a vapor. That's one advantage here. But there are some better methods are there than this first method. The method is a Williamson synthesis. Williamson synthesis of ethers. You can say Williamson synthesis, then the question comes, synthesis to what? So better say Williamson synthesis of ethers as a single name, so in which the ethers preparation is there, so therefore you can recollect immediately. In this method, what Williamson did is, here in this alcohol water is eliminating, right? Now see the concept here, one alcohol is converted into the alkyl chloride by adding like PCl5 or PCl3 or thionyl chloride. One compound is converted to alkyl. The other alcohol is converted into its sodium salt. not by adding the sodium hydroxide. Sodium hydroxide cannot convert. Phenols can be converted into sodium salt, but alcohols only method is sodium metal. Direct metal if you add, then alcohols will convert into this one. Now if you two add up, then you will get the diethyl ether. This reaction has a number of advantages, like first advantage is there is no necessity to heat. Here the heating is there. So therefore first advantage, no heating is required. Second one, catalyst is there. Here no catalyst. So second is no catalyst is required. Okay. And similarly you have a eliminating molecule is water. Here eliminating is NaCl. Okay. So the NaCl formation will have a more ready to form than the water formation. So therefore the high percentage will be there. The percentage of the reaction will be very, very high, surprisingly, and there is no side products like this, all this ether formation and sulfate formation, ethylene formation will not be there. And this reaction happens to be the alkoxide attacking and the Cl going out is a characteristic reaction of alkyl chloride, a nucleophilic substitution reaction. So the alkyl halide is undergoing its own, that is characteristic reaction. So the reaction has got a very good facility for the formation of this reaction. It has finally one more special point here, that is if I want both alkyls same type like ethyl and ethyl, you can, but one side ethyl, one side propyl, that is called what? Mixed ether. Two different alkyls containing is called mixed or unsymmetric ether. If this unsymmetric ether, if I want to prepare from the first method, an example, for example, methanol and ethanol I will take, and I would like to prepare what? A propyl, that is methyl and ethyl containing ether I want to prepare. But there is no guarantee that all the molecules turn up into this product. In addition to this compound, you may get a methyl as well as ethyl ethers also. So finally what comes is, this is called what? Mixed ether. Mixed ether means two different alkyl groups containing, right? But whereas what you get is a mixture of ether. Mixture means a ether in which two different, 2, 3 or more different varieties are there. So you got a mixture of ethers. So our aim is to prepare pure mixed ether, but we got a mixture. To avoid this mixture formation, Williamson is the best method. That is, for example, in the case of this particular methyl and ethyl, one of the compound like methanol, for example, methanol you convert into the methyl chloride, and another one is ethanol. Ethanol you convert into sodium salt, that is a methyl chloride and a sodium ethoxide. If you take only one compound, that is methyl ethyl comes, that is a perfect method for the preparation of the pure mixed ether. That is the advantage is pure mixed ether. Pure mixed ether. The word looks little ambiguity. What is pure and what is mixed? Mixed means two different and pure means single. What is two different means two alkyls are different, but I want in the form of pure one, that is only one compound should be there, isn't it? So pure mixed ethers preparation, Williamson synthesis is the best one. Williamson can also be used for the aromatic ethers also. Aromatic ethers for taking phenol and ethanol, getting a that is ethoxy phenol or methoxy phenol, that type of aromatic ethers preparation has got much more less product formation. But whereas in the case of this Williamson synthesis, for example, if you convert ethyl chloride, ethanol into ethyl chloride and then take sodium salt of the phenol, only thing is you have to choose which should be the alkoxy, which should be the alkyl halide. Better go for the ethyl chloride. I'll show the methodology. For example, for the preparation of mixed ethers, mixed ethers, I want to prepare a ethyl and a methyl ether, right? In such a case, you have two options. One is taking methyl chloride, adding the ethoxide, sodium salt of ethox. So, methoxy will attack here and create this Williamson synthesis, will generate the ethoxy methane. You too can take the other combination, that is ethyl chloride taking the sodium salt of the methoxide. Okay, this methoxy will attack and show, but the methoxide is also a strong base, isn't it? So therefore, a small quantity of this one may also go to the formation of some ethylene formation. This is what side product, isn't it? Because ethyl chloride may undergo elimination influenced by the stronger base ethylene, but in the other method methyl chloride cannot have any that type of the problem. So in the mixed ethers preparation, you have this type of the discussion. Similar the way, if I want to prepare a methyl and methoxy benzene, you can go for the two methods. You can take methyl chloride and take the phenoxide, that is sodium salt of the phenol. You can take as a anion is phenoxy, and then attacking on the methyl chloride, you will get this product. Or you can also propose another method. What is that? You can take a phenyl chloride and take the methyl salt of the alcohol, that is methanol should be in the form of the salt, sodium salt of the methanol. If you take methoxy group is attacking and showing this one. But out of these two, which is the best method, means this is the best method, this is not proper method, because phenyl chloride is an aromatic one. Aromatic halogen compounds will not undergo nucleophilic substitution that fairly because of the stabilization of the chlorine with the phenyl showing resonance, and the alkoxy group attacking an aromatic system. It is electron rich system. The chlorine outgoing property, because of the plus M effect, it is not the, here it is only minus I effect in flame, no plus M. Here plus M effect, double bond character, so cleaving is difficulty. So aromatic halogen compounds will not undergo nucleophilic substitution fairly. Therefore, this is not a good method. Anyhow, the product is same, and the byproduct also will be the same, in fact NaCl only. If the byproduct changes, then the more the stability of the byproduct, more will be the yield. That is the concept of Williamson synthesis. However, in the both the reactions we get NaCl only, but the reactivity of the alkyl halide versus aromatic halogen compounds, alkyl is better. So therefore, take the alkyl halide and the aromatic in the case of that is sodium salt you take, not the aromatic halogen compound and the aliphatic alkoxide. Okay. Here both are aliphatic. In such a case, see that the primary compounds should be in the halogen case, tertiary can be in the form of salt. Primary, tertiary, or primary, secondary, or primary in the compound which may undergo elimination always take that side. Smaller compound which will not have any elimination problem, select in this side, then you will get the better yields of this react. This is only a comparison of when 2-3 chances are there, all are Williamson concepts only, but out of the 2-3 methods, which will be the best method may be the question are discussed. For aromatic ethers, we have 1 or 2 special methods, like for example, you take a aromatic compound and add a dimethyl sulfate. Dimethyl sulfate, a methylation takes place, you will get the anisole formation. This is a damn easy reaction, because the 2 moles of phenol will be reacting and making this one and liberating the hydrogen. Sulfate of the H2SO4 will be formed. That is called anisole preparation, will be very easy. Even diazomethane, CH2N2, is a gaseous compound dissolved in the ether, added to the phenols, you will get the similar type of the reaction, but the eliminating product will be the nitrogen gas will be out. So anisole will be formed as a one of the chief product. The diazomethane is also good reaction, but both the reagents can also be used to prepare esters from the acids. are COOCH3, a methyl ester. So therefore, we have an advantages. If there is a COOH that I want to esterify simultaneously, you can also do it. All the acids with the same both the reagents, acids can be esterified also, just like phenolic OHs are etherified. Simultaneously, both the reagents can be used for the esterification also. Similar reagent it is in the case of acids, you will get esterification. So this is specifically used in the aromatic ethers preparation, which is not for the aliphatic alcohols to ethers, it is not useful. Let us take some points on the properties of ethers. One must know that the ethers are very stable and they are almost inert to the several types of the chemicals, and just like casual acids and the bases generally will not react with the ethers. Ethers are quite stable. The reason being, in the alcohols the O is attached with hydrogen. That hydrogen is very reactive. In the alcohols you see ROH. This hydrogen is quite reactive because the bond breaks easily and the energy required to break this OH is very easy, and then that hydrogen will become very reactive towards sodium and so on. But when both the sides alkyls are there, oxygen is there. Oxygen is in fact very reactive element, but both the sides it is attached with the carbons, then just like a loin in the cage will become almost silent. Like that, this oxygen has been binded by the both the side carbons. Most of the reactions of this oxygen is silent. It is so quite a number of times the questions are asked why the ethers are very less reactive or more inert. Why? Explain the inertness of the ethers, which makes the ethers to use as a solvent. That is, it won't participate in reaction, therefore ether is considered to be a very good solvent. Why? Means it is the reason that the oxygen is reactive, no doubt, but binded by both the sides carbon, so therefore it will become non-reactive. Specifically, the reagents like the ethers will not react with the dilute bases, NaOH, no reaction, okay, and concentrate base, no reaction, even concentrated also no reaction, right. In the third case, ethers practically almost concentrated acids also no reaction. But one may write like this, for example, concentrated sulfuric acid is added, what happens? Actually there is no much reaction, but the ethers are get protonated with the proton, a plus is formed. Consequently, the HSO4 will be the side by. What is the then significance of this salt? Means the whole thing will become soluble in concentrated sulfuric acid. So ethers are soluble in the sulfuric acid. That is the one point you have to note it. Concentrated sulfuric acid, ethers are soluble. Most of the organic compounds are soluble. Actually, solubility with reference to the sulfuric acid, you need not to check, you can take it grant all organic compounds are soluble, except in some cases. What are insoluble in the concentrated sulfuric acid? Means alkanes are not soluble, and benzene and alkyl benzene, that is arenes. These two, when I add concentrated sulfuric acid, no reaction. But ether is soluble. Ether and these hydrocarbons have got some similarity in the inertness. But how do you differentiate? A good question is, in the alkane we have a alkane specifically N-hexane. This is called a PET ether. PET ether means it's a ether-like behaving compound from petroleum products. So it's called PET ether, used in the dry cleaning of the cloths. Okay, N-hexane it is. And other one is ether I will take, that is 2 carbons with oxygen. This is normal ether. Ether and solvent ether, otherwise it is, you call it as a solvent ether. So both the sides ethyl group is there. That ether is called normally solvent ether. Solvent ether. Get the solvent, or I want solvent. That means it is the ether actually. In the ether bottle, ether is written small letters, but the solvent will be blown up shown, because it is a wonderful solvent, universal organic solvent. It is ether actually. So solvent ether and petroleum ether or pet ether, how do you differentiate? This is a beautiful question. Now add the concentrated sulfuric acid for both. In the case of the petroleum ether, it is not soluble, negative. In the case of the ether, it is plus, that is soluble. So pet ether is soluble in the constant sulfuric acid. The reason is protonation, no chemical reaction, just protonation. This is at room temperature, however. If you heat it to beyond the 140, that is specifically at 170, the ethers too undergo elimination to give the alkenes. So therefore, at room temperature, if you add sulfuric acid for both, one becomes into soluble, that is ether gets soluble. Petroleum ether is insoluble. The negative shows insoluble, positive shows soluble. So soluble, thereby one can differentiate these two. The both are inert, will have some similarity, and alkanes also not reactive towards acids and bases. Ethers also similarly, as I said, both bases it is not reactive, and concentrated acids also just protonation takes place, salts are formed with the hydrochloric acid or sulfuric acid, just salt is formed. Then consequently it is absorbed, that is dissolved, but the chemical reaction, you see, excepting the protonation, the ether bond is not open. However, with dilute acid it reacts. Dilute acids, however, hydrolysis is taking place. So therefore, all ethers, when I add water in presence of the H plus, reaction taking place. What is that reaction? It cuts into two alcohols are formed, two ROHs, that is called hydrolysis. This is possible with the acid medium. So therefore, dilute acids can open the ether bond successfully. The process is called hydrolysis. Concentrated acids, just protonation takes place, salts are formed, that salts are shows the solubility in the sulfuric acid. So out of the two bases and two acids, two bases are not having any reaction. Concentrated acids make only salt formation, but dilute acids they undergo reaction, right? Hydrolysis. Even with the mild oxidizing agents also, mild oxidation, the ethers have no reaction. ROR with mild oxidizing agents, no reaction, like a Tollens reaction, all such mild oxidizing agents, ethers will not undergo any oxidation. Permanganate or that is Bayer's reagent, for example, nothing happens and the ethers are quite stable. So the stability is also can be explained through this particular oxidation. Bayer's reagent has no reaction, whereas alkenes open up, you will get glycols formation. Alkynes also open up and you will get aldehydes or ketones. So like this, ethers are silent with the number of mild oxidizing agents, that shows the stability of the ether. So finally what we want to say is ethers are quite stable. That's why acids, bases and mild oxidizing agents have no reaction. But acids in presence of water, that is called dilute acids, can open up the ether. They show hydrolysis to give back the alcohols. From the alcohols only we prepared. In fact, they hydrolyze back to give the alcohols. There are some specific reagents, however. Among the reagents, the first and the best reagent is hydroiodic acid. HI will readily react. Which chemical or which compound reacts readily with ethers means the HI. Specifically, even the sodium metal, no reaction. Several compounds react with sodium, but ethers are not going to react. That also can be noticed. The reagent that attacks readily is HI. So therefore, the best reaction is hydroiodic acid. So let's see some specific reactions of these ethers with reaction with HI. This is what somewhat important reaction over the all other reactions. The HI has got two different types of the conditions. Ethers may be opened into two types. That is with HI in the form of 1:1 ratio, or people also say dilute HI or cold condition HI. The other HI is excess of HI, or people also say concentrated HI. Some books are saying hot HI. In all these conditions, the reactions are taking place 1:2 types of the, that is 2 HI will break both the sides. In the case of 1:1, so only one side breakage takes place, one becomes into alcohol, one becomes into alkyl iodide. Whereas excess is there, even this side also cut and 2 moles of alkyl iodide is formed. The oxygen will become into the H2O. So there are two clear cut the reactions are there. If low amount or 1:1 HI is added, only one side breakage takes place. You will get one side alcohol and alkyl iodide. Excess is used or concentrated is used or hot condition of the HI is used. Both the sides ether bond opens up and both will become alkyl iodide and the middle oxygen will become to H2O. This is a clear information. However, if excess HI is used, both are becoming into alkyl iodide. So therefore, there is nothing to discuss on this one. But in the case of this 1:1, which R becomes into alcohol, which R becomes into alkyl iodide is a question now. So on this specific issue, we have some questions like different types of the alkyls are taken, like R1 and R2 is taken. Different alkyls are there. Will the R1 becomes into alcohol or alkyl iodide? That is the question that we have to take in details and we have to discuss. Like for example, if a ether containing one side tertiary, one side primary is there, right? Okay, one side tertiary, one side primary. Then the breakage can be, if the case is that is a 1:1 ratio of HI if it is added, you can have two types of the breakages. The breakage this side gives the carbocation on the tertiary, and this will become into the ethoxy group, ethoxy and carbocation type breakage. Break between the carbon and oxygen. Definitely the 2 electrons goes to the side of the oxygen. So you will get ethoxide anion and the carbocation will be the intermediate. After that, the carbocation is stabilized because of what 3 degree it is. 3 degree carbocation will be the stabilized one. So therefore, this breakage has got some favorable factor. But if I break like this, then what happens? Ethyl carbocation is formed, and then the other side is a tertiary butoxide. Tertiary butoxide will have a destabilization. So therefore, tertiary butoxide is destabilized. Ethoxide is not much, but already minus is there, all the alkyl groups are plus I effect means destabilized. So therefore, this pattern is not encouraged. So always so that break in such a way that the alkyl becomes into more stabilized carbocation. This side ethyl carbocation, this side tertiary butyl. Best is always tertiary butyl, 3 degree carbocation. This side 1 degree carbocation, you will get this also stabilized, not much. When compared with this 1 degree carbocation, this is a 3 degree carbocation, more stabilized, therefore a favorable factor. So always a tertiary butyl will become into carbocation. Subsequently, the carbocation will take the I minus and ethoxide will take the H. If ethoxide take the I, you will get a iodide salt of that. That's not correct, isn't it? We get alkyl iodide. So this alkyl will take the I minus and the tertiary butyl carbocation. You will get tertiary butyl iodide, and this will become ethanol. So this is the major quality goes. In the other side breakage, that is ethyl becoming into iodide. ethyl iodide formation, and the tertiary butyl formation, alcohol formation will be the less quantity will be there. This will be the major quantity. So this question several times comes, that the breakage always goes towards the, if both are alkyl, the tertiary will be the given a preference to become a carbocation, therefore this breakage will be the correct one. So if two different alkyls are there, the second type breakage, that is becoming into ethyl carbocation, giving this ethyl iodide, is not a favorable one. Ethyl carbocation also stabilized, but it is 1 degree. Tertiary butyl is a 3 degree, therefore always a favorable formation for the first type of the possibility, that is tertiary butyl iodide and ethanol will be the major one, and ethyl iodide and tertiary butyl alcohol will be the minor products will be formed. So similar the case with the, if ether is between aromatic and the aliphatic, aromatic and aliphatic case also can be discussed when you are hydrolyzing with the 1:1 HI. There are two types of the breakages. The breakage can be between the phenyl and the oxygen, or ethyl and the oxygen. Let us call this is the first type and this is the second type. In the first type of breakage, you will get phenyl carbocation and ethoxide anion. Both are destabilized, both this side, that side. This is destabilized because an aromatic system requires a thorough flow. On an aromatic system, carbon, if it becomes carbocation, electronegative element becoming positive is one problem, and electron flow, whenever carbocation is there, that the flow will have a threat. So therefore aromaticity will have a threat whenever the carbocation is formed. So therefore the benzene becoming into a phenyl carbocation is not a favorable one. Ethoxide, this is ethyl carbocation is stabilized, but the ethoxide is destabilized. So both the sides we have a destabilization factors. Whereas a carbocation formed on the ethyl and the anion formed on the phenoxy group, now the breakage 2 will give the ethyl carbocation and the phenoxide anion, both are stabilized. Phenyl with anion stabilized through the resonance, okay, and the ethyl carbocation stabilized through the plus I effect and the hyperconjugation. Both phenomena shows that ethyl carbocation is stabilized, phenoxide is stabilized, whereas here ethoxide anion is destabilized, phenyl carbocation is stabilized. Therefore the first method is not acceptable from both the sides, whereas second method is acceptable from the both the sides. So therefore always major product goes to the ethyl iodide plus phenol formation. Whereas the other option we have, what is the other option? Phenyl iodide plus ethyl alcohol. This is a lower percentage. Always the major percentage goes to this ethyl iodide and the methane. That is what when aromatic system is attached with whatever the type of alkoxy, whether it is methoxy or ethoxy, all that alkyl groups will become into alkyl iodides, and aromatic systems goes into the phenol. That is in general observation. So therefore there is one procedure is there, like for example in the nature we have some aromatic systems containing some alkoxy groups. You need not to say what group also. So let me mention the methoxy groups however, but need not to be methoxy, it can be ethoxy, and the mixture of methoxy also can be there. So an example, if this is an unknown compound whose total structure is not yet known, but its molecular weight is identified through the physical concepts. So weight is known. So how, let us take some x grams of this compound divided by its molecular weight will give the moles. So how many moles I am taking should be very clear. In this case little excess of HI if you add also no problem, Actually, we are having a 1:1 ratio. Little excess of HI also no problem, because always the alkyl becomes into carbocation, subsequently react, and they become into the alkyl iodide, and this compound goes into the phenol formation, that is all the OCH3 will become into OH and OH and OH, right. So, wherever the OCH3 are the OHs, but the alkyl groups will become into alkyl. How many? For each mole you will get 3 moles of methyl iodide. This methyl iodide not treated directly silver nitrate, but fused with the concentrated HNO3, so that the I minus is released, subsequently added with the silver nitrate AgNO3. Then all that I will react with silver and you will get silver iodide precipitate. This is a yellow color precipitate. Now, how many moles of silver iodide is formed experimentally, because it is a precipitate, to filter it and take the weight of that silver iodide. Silver iodide weight by its molecular weight will give the moles. Let us start with the 0.01 mole I have taken and resulted in the 0.03 moles. How many moles of silver iodide means 0.03 moles. Taken 0.01, that means 1 mole giving the 3 moles. Therefore, immediately we can say that there are 3 alkoxy groups are there. Therefore, 3 alkyl iodides, 3 silver iodides are formed. So, this method is known as G-cell method. G-cell method of estimation of OR groups, or you can call it as a alkoxy groups. Alkoxy groups can be estimated. This is called G-cell method. G-cell method of estimation of alkoxy groups. The groups can be, some can be methoxy, some can be ethoxy also. Both gives the alkyl iodide, and then final product will be the silver iodide. So, how many moles of silver iodide is formed? Out of how many moles I have taken, see the ratio and see, and 1:1, 1:2 or 1:3 like that, then you can decide how many alkoxy groups are there. Just like reactive hydrogen estimation, this is a alkoxy groups present in a given compound can be estimated. The method is known as G-cell method. So, that is basically principle is here. Whenever aromatic, aliphatic are there, aliphatic will become into alkyl iodide. Aromatic side you will get the alcoholic group, right. So, because of the, that's a carbocation present in the reaction. 1 or 2 less important reactions also there with alkyl ethers react with carbon monoxide in presence of some Lewis acids, they become into esters. Esterification takes place. The CO group is inserted and you will get a CO with OR, ester is formed. So, ethers can be converted into this one. This is the one of such reaction with alkoxy, that is ethers will react with the phosphorus pentachloride. They react and gives the 2 alkyls into 2 alkyl chloride plus POCl3. In this also ether bond is open up. Ethers react with Grignard reagent, not with specifically, but ethers makes a non-polar complex like magnesium being the central metal ion. Both the sides ethers are covering. This is a specific complex called a non-polar complex, in which the metal ion is in the compound, not as a pure ion, and the ligands are ethers. Both the sides ethers will encircle this Grignard reagent. In fact, in this reaction you can say the Grignard reagent is stabilized. So, many times Grignard reagents are stored under the ether. Why? Because means the Grignard reagent is covered by ether, both the sides acting as the ligands, and it will become a complex compound in which neither on the middle compound and ligands, total charge is neutral, there is no charge. So, no charge or the non-polar complexes are formed through this the particular reaction. This finally the result is a stabilization of the Grignard reagent in presence of the ether. Ethers will not react with the sodium metal. However, the hydrolysis of ethers have got small point, specifically in the cyclic ethers we have 1 or 2 points. Ethers undergo hydrolysis acidic medium as well as basic medium. So, basic skeleton reaction is like this. They react with water either with the acidic medium or with the basic medium. Both reactions takes place and you will get 2 moles of alcohol. Here also 2 moles of alcohol. Basic reaction is very simple, but the mechanism of the reaction slightly differs. With reference to specific example, let us take a cyclic ether containing this side 2 methyls are there. This is the specific example which suits for the explanation here. 2 methyls containing ether I am taking, doing the hydrolysis in the acidic medium, that is H plus with water. Acidic hydrolysis I am doing. First the proton will attack on the lone pair of the oxygen. Okay, this is called protonation. So, subsequently what you get is a protonated compound, that is a proton is added, O will become the O plus is formed, oxonium ion is formed. Now, we have 2 chances. These 2 electrons will be withdrawn by the oxygen so that it will become OH. This carbon may become into the carbocation. Okay, breakage is this side, so that carbocation is formed. So, we have the 2 intermediate formation from here. So, you may have an alcohol on the middle carbon, carbocation on the terminal carbon, or these 2 electrons may be withdrawn and the breakage can be this side, so that a tertiary carbocation is formed and a OH goes to that side. Okay, either one may be possible. Now, I will leave this question to you, which will be the more stable. Naturally, one can accept that this is a 3 degree is more stable, right? So, whichever the carbocation comes on hydrolysis. Now, the water molecule using the lone pair will attack here or will attack on this carbocation, and then it leads to give the proton will come out and OH will settle. Finally, this side 1 OH, that side 1 OH. So, both will become the alcohol. So, final answer is very clear that so each carbon gets 1 OH. Only thing is, with reference to the stereochemistry, if you want to discuss, one side the H plus has come. So, therefore, water comes from the downside. Definitely anti-type of the addition takes place, and you may write 1 OH up, 1 OH down, but this is a single bond. So, therefore, it rotates. There is no much significance even if you write 2 OH and claim that is anti-type of alcohol is formed. But in the system like a cyclotype, for example, if this is a cyclotype of compound is there, definitely this reaction leads to give the anti-type, that means 1 OH will go up and 1 OH will come down. So, this leads to first the epoxide formation. So, make 1 epoxide formation and then subsequently make hydrolysis. So, 2-step reaction, first epoxide, make a epoxide and then hydrolyze it with the acidic medium. You get the glycol's anti-type because of the approach of the proton from the opposite. So, you will get it. But when it is single bond, there is no much significance, it rotates. Therefore, let us write on the same side or opposite makes no difference. In both the cases, you will get the glycol. But the point is very clear that which side carbocation mechanism is more correct means the lower one is more correct and this one is not correct. And the significance of this particular observation is, if at all the water molecule added is O18 O18 means normal oxygen will be 16. This oxygen is a isotopic one or labeled water I am taking. don't take labeled hydrogens, labeled oxygen is taken here. Now where comes that? Old one is in the epoxide is the 16 one. Now new 18. Will the new 18 this one or this one is the now the question. So according to the mechanism, the carbocation formed will be the tertiary on which a new 18 will go and add, right? So 18 one will go to the center. So therefore this will be your U18. Both the sides you won't get 18. Original O goes to the terminal so that the tertiary carbocation is favorable one. Then the new 18 will be added to the center carbon. So we be clear that in acidic medium when you hydrolyze, it passes through the stable carbocation and then leads to give the on the stable carbocation water attacks, that is newly added water comes. So newly added O18 goes to the center carbon, right? Is it clear? Yes. The same type of the hydrolysis in the basic medium, that is in the basic medium OH minus and water. You too can use alkoxides also, okay. This water also let us labeled one now, okay. So what is attacking is now not the proton, there is no protonation in this mechanism, right? Is it clear? There is no protonation. The whole water using the lone pair is going to attack on the system. Now we have two chances. Should I attack that water on the terminal carbon or in the middle carbon? So first nucleophile is attacking there, electrophile is added, that is a positive species. Directly either the OH minus or the H2O, they are in equilibrium. In fact, if one is O18, it is understood the other one also O18. It is understood as a this is the default. If it is not labeled also, it will become labeled because of the exchange of this one. One is labeled means the other one also you have to take it grant. So therefore, if 18 is there here also, obviously you have to take 18 only. So therefore, this water molecule can attack this one or this one. Now nucleophile, where it will attack means where the electron density will be less. So this carbon has two alkyl groups and this is one alkyl group. Only one is withdrawing, three are donating. Whereas to this carbon is donating, this is withdrawing. So here more donating groups are there. This will become electron rich, it is. More electron density will be there on this carbon, less electron density will be there. So this is a minus group preferred to attack on the less electron density. Less electron density it will attack, not on the more electron density. Therefore, the newly added O18 goes to the terminal carbon and then later it opens, becomes into O minus and then react with a water, takes the proton, leaves the OH minus. So, but the final compound will become now like this. Here also two OHs will come, specifically anti position only, but there is no point in writing anti as I said. So the O18 goes to the terminal one. So difference between that and this with labeled one, one can easily identify. Both becomes glycols, okay. But even both are anti only. As I say, I have written same side, but it is single bond, that's why I have written same side. But this O18 will be in the center if it is in the acidic medium. If it is in the basic medium, O18 or alkoxy group, if I used OR will come, that goes to the terminal carbon, that is 1 degree carbon takes that O18. That is the fundamental difference between this and the acidic medium and the basic medium hydrolysis.